Now we come to the component formula for the dot product, which is actually a lot easier to apply. But our syllabus says that we need to be able to demonstrate how the component formula can be derived from the geometric formula. So we'll follow that through now. Now, as long as you've got this triangle as a starting point, and I'm assuming that most questions asking you to do this would give you a triangle to use where you've got some sort of parameters already in place. And you can see here that this triangle is quite straightforward. We've got vector A and vector B going in this direction, so that makes this one vector A minus B. Once we have that triangle, all we really need to do is apply the cosine rule to it. So no matter which version of the cosine rule you use, either the one that finds angles or the ones that find sides, you're going to get to something sensible. So if we start with the one that finds sides, then we could say that we could take this side here, which is just the length. Remember that finding the absolute value of a vector just finds how long it is. Now this squared is equal to the other two sides squared and added together minus 2 times one side times the other side times the cos of alpha. Now there should be part of this which is going to jump out and look familiar. This part here, a, b cos theta, with these in absolute value brackets, this is what we've just defined as the geometric formula for the dot product. So we can rewrite this then, and instead of that last section, we are going to write the dot product. Oops, we needed to square that one. Minus 2 lots of the dot product of A and B, and we get that. Now we can just rearrange this to get this part by itself. So adding 2 lots of the dot product to both sides, we've got this, and we'll get this side squared plus the other side, whoops, squared. It's very easy to leave out a squared sign or a squiggle or something, so as you're doing this, just check your work every now and then. Now you're probably thinking that the next step would be to divide everything by 2, but I'm not going to do that, and you'll see why in a moment. From here, I'm going to say, all right, well, what is the absolute value of vector A? In other words, the length of vector A squared. What's the length of vector B squared? And what's this length squared? Because if I can come up with these in component form, then I'll have a component formula for the dot product. So this is easier than you might think. Let's just give A some component vectors. So all we need to do here is say, well, if this is vector A, how far across are we going? How far up are we going to get from where the vector starts to where the vector finishes? So we could just let this distance across here, which I can sort of dot in like this, be x1, and this height here be y1. And we can write it really simply in column vector form, or we can write it like this using the i's and the j's. And then we can let vector B be over here, and it's got a certain x2 and it's got a y2. Now on this picture it looks like it's going in a negative direction. Don't pay too much attention to that. If it's going in a negative direction, then x2 will be negative. This is just a basic picture. We could have A over here and B over there. The negatives and positives can be wherever they fall. So now we've got actually a little recipe for vector A and vector B. Now, if you wanted to find the length of vector A, what would Pythagoras do? Well, you've got a little right angle triangle here, and we've already seen how to do this in the previous exercise. We say that this length squared is equal to this length squared plus this length squared. So, jotting that down here, if we have x1 squared plus y1 squared, that will give us vector A, the length of it, squared. Now, there's no point taking the square root of that to find the length of vector A because we're squaring it anyway. So we can now go ahead and sub this straight in over here, and we will have 2a dot b is equal to x1 squared plus y1 squared. And then for the other vector, we can do the exact same thing, except it's going to be x2 squared plus y2 squared. And now applying the distance formula to find the distance of this vector, all we need to do is say, well, how tall is this length here? It would be y2 minus y1, and we need to square that. So let's rub this out here so that we've got a bit of space to continue our working. Now we're subtracting something complicated, so we're going to need to use brackets so we don't make a sign error. We need to do y2 minus y1, and we need to square that, and then we need to add it to this length, which would be x1 minus x2. Now, if x2 is negative, subtracting the negative, that'll add those together, and that's effectively finding the length here. So we've got x2 minus x1 all squared. Next, I'd like you to pause the video and have a go at expanding this part out yourself, making sure that you don't make any sign errors there, and then gather up your like terms and see what you get. So I've gone ahead and I've done mine. I've kept brackets around this whole part here, and now rather than expand those again to write it all out, I want to save a bit of time. I can see I've got an x1 squared here, but I'm subtracting an x1 squared over there. Similarly, my x2 squareds will cancel out. My x1 squareds will cancel, and so will my y2 squareds. Where's that one? Here. And all I'm ending up with is subtracting minus 2y1, y2. So that means I've got 2a dot b is equal to 2y1, y2 plus 2x1, x2. Now, I had the y's first. You could easily have the x's first in here. It makes no difference. I just literally applied Pythagoras' theorem rather than memorizing a formula. And when I used this formula, I went for height first. That's the only reason that my y's are ahead of my x's. Let's tidy this up now. And now you can see how easy it is to divide all three terms by 2 and say that a dot b is equal to, let's write the x's first. It's x1, x2 plus y1, y2. Now, this is the component formula for the dot product. So it's ended up kind of small and at the bottom of my page, but this is important now. Let's put a big box around it or highlight it, whatever your system is. This is our component formula for the dot product. So this is the formula that we just derived, and we can alternately write it with column notation, knowing that if these are just vectors, which must have their own x and y components, then if we were writing the vectors in component form in the first place and finding the dot product of them, then we get this very simple result. Multiply the x's together and then add the multiplication of the y's. Now, if we put the component form and the geometric form right beside each other, this is what you have on your reference sheet. So you don't need to memorize either formula, but you need to be able to apply both of them, and you need to be able to derive this one from that one. You'll also see that you can play the two formulas off against each other to find angles if you know the components, and vice versa. And now an example. In this diagram of triangle AOB, vector A equals OA and vector B equals OB. So they're going out in that direction. We've got the points -3 and 3. We're on a Cartesian plane, and we've got the point 3√3 up here. So we need to start by finding all three of these as column vectors. Now you'll notice different notation here. These are written in vector form with the little squiggle underneath, and this one's written as a directed interval. All three are vectors though. So for AB, we could add an arrow to our picture up there. So vector A, we just write as a column what is the action required to get from its tail to its head. So to get from here to here, you need to go 3 steps to the left, and that means that you need an x value of -3. We're going left, and then we need to go up 3√3. So once you get the hang of this, it's really quite straightforward. Vector B, well, how do we get from the tail to the head? We go 3 units to the right, so that's +3, and then up 3√3 units. And then vector AB, well, to get from here to here, we need to go 6 steps. So I think the easiest thing here, once you've got your picture, rather than doing 3 minus -3 and messing around with signs, just literally look at how you'd instruct someone to get from the tail to the head. And the vertical movement is 0. So now that we've got our x and y components, finding these dot products should be really straightforward. In fact, a lot easier than using the other formula. And before we get started, I've jotted down the formula over on the side here so we can remember what to do. And I've used u's and v's there so that when we're subbing in 2 a's or an a and a b, we're not confused about what to do. So we've got our x's and y's just sitting here ready to go. So a dot a just means we need to do -3 times another -3, and that will be 9. And then the y's multiplied together, 3√3 times 3√3, well, that's 3 times 9, which is 27. So we get 36. And remember, what we're looking for with the dot product is a scalar quantity as our answer. We're not looking to make another vector, so don't try and put it in column form or anything like that. Just follow the recipe and out will come the solution. Okay, so now doing these two, we need to multiply the x's, so we get minus 9, and then multiply the y's, we'll get 27 again, and so we'll end up with 18. For this one, that shouldn't be a dot, that should be a little squiggle. We need to do this and this. So multiplying the x's, negative 3 times 16, you can see how simple this is once you get the hang of it, and this times 0 is just 0, so we get negative 18. Now, you might be thinking, why am I bothering adding things together here? When you're getting the hang of the process, I would recommend this line of working because it's just reinforcing what you're actually doing rather than jumping straight to the answer. It's reinforcing the process. Now, for this last one, we've got some choices. If we want to look at what a plus b is, if it was something we could turn into another vector on our picture, we could do that. But look, a plus v, they've got the same tail. So there is no other vector on our picture that's easy to use for that. So we're better off using the distributive law here and saying this is a dot ab plus b dot ab. Now we've already found a dot ab, that was negative 18. So this part's negative 18 and that's done. And this part we need to do b dot ab, so that's these two. So again, multiply the x's, and we get 18. Multiply the y's, and we get 0. And now we've got negative 18 plus 18, and we're going to get 0. Now, this should be a red flag. What does this mean? It means that this vector and this vector are perpendicular to one another. So when you get this solution, just check that that looks right and that does actually make sense. Let's think about what vector A plus vector B would look like. So I've just drawn it again lower down on my board so that I can actually fit it in. If this is vector A and this is vector B, then if we want to do B and then add A on, it's going to go up like this. And this length will be the same as this one, and it will of course be parallel. So you can see that it's going to take us to a point here that is directly above there. So what we're finding then is that B plus A, which is the same as A plus B, is taking us from here to here. This is the vector A plus B. And clearly it is perpendicular to AB. So that makes sense.